Vivek, are you able to hear me clearly?
Yes, yes.
Yeah, and then
Uh,
so good evening, friends. This is Prakash. Thanks to Cellstrat for giving me opportunity to talk on the GPU compute platforms on AMD for AMD GPUs, and we have designed this specifically for deep neural networks. This stack is actually called ROCm, as it can be seen on the screen. So the agenda for we will have some discussion, maybe question and answers as we go along. I'll try to answer the questions as we go along. But if you have more questions, definitely we will take it at the end of the session. I intend to not to speak more than maybe 45 to 50 minutes, and then we can spend some 10 minutes for Q&A if you have any. Yeah. So I know Vivek and Vishal are conducting a series of webinars on deep neural networks. And this webinar is slightly different from what probably you may have heard from them, because this is more of the compute platforms, the enabling platform for developing and deploying deep neural networks. As you all know, GPUs is one of the biggest enablers for deep neural networks, because the GPUs can compute very fast compared to the CPUs, and probably 20 to 30 times faster. And that's the reason why deep neural networks GPUs are preferred for DNN, especially for training, and both and for inference as well. Now, AMD also has a stack which can be used for developing deep DNN applications and for the inference. So this webinar essentially is to introduce you all to the ROCm stack for AMD platforms. That's the first agenda item. And we will also introduce what are the language support we have for ROCm for the GPU compute. The first two bullet items are nothing to do with deep neural networks as per se, but it is the software, the language support and software for developing any high performance applications. Deep neural networks is one of them. Then we will move on to see how we can how we can develop or port deep neural network applications on the AMD platforms using the ROCm stack. And the fourth one is we will also see what are the what's the work already done by AMD to position AMD platforms for DNN deep learning software. And we will also see what are the frameworks which are available. I will give you the link where it can be downloaded and you can try on AMD GPUs. That's essentially it. I don't have too many slides. I have about 12 to 13 slides, so we should be done very quickly. Okay, so let us get started. You may all I'm sure you all know about AMD GPUs. AMD GPUs are more known for gaming and workstation kind of applications. But recently we also have this deep neural network stack following NVIDIA. Essentially what we how we differentiate from other competitors is with respect to performance. As the first says performance. We match teraflops of performance, and then we can give you high performance for deep neural networks. And second important point is all the whole software stack is all open source from AMD. There's nothing proprietary about it. We have put everything on the GitHub, so you can download, you can make any changes, and you can actually submit to the code. So when I say the whole stack, I mean the drivers, which is essential to access the GPUs, and the compilers, and then the runtime, and then the language processors, and in fact the DNN frameworks. All complete stack is open source. And the third point says that we are ready for hyperscale as well, which means that we can actually look at scale out options for deep neural networks, where you have connectivity like Gen Z from HPE, and we can actually scale out to maybe hundreds of nodes as well. So our stack enables that. So I know there's a lot of text in this slide, but essentially, what is ROCm? How is it different from other software, other GPU compute software? So the first essential, the top left corner is the driver, which is a headless Linux 64-bit driver, We support a large memory, a single allocation. We support multi-GPU peer-to-peer communication, which is very essential for deep neural networks when you are trying to do some model parallelism or the data parallelism. And we also support RDMA, which is remote DMA across server nodes. That's again essential for when you have a scale-out options for if you have, let us say, there are 10 servers, each having 2 GPUs, we can actually do the training parallelly. And we have obviously system management APIs and tools. On the right side, on the top, we have what is called as HSA. HSA is a consortium led by AMD. It is called Heterogeneous System Architecture, which actually which was awarded about 7-8 years back, where that gives you a way to interface with the GPUs, how efficiently, how effectively you can interface with the GPUs. As you may know, the operating systems like Linux or Windows do not recognize GPUs as first-class citizens. They know only the CPUs. To access or to schedule any workload on the GPUs, you need the native driver from the vendor who was given the GPU. For example, in this case, AMD. So the HSA driver is the driver which is given by the AMD. It is again an open standard where we sort of we have defined as a consortium. It's not just AMD. We have a consortium with a few other companies, where we give, for example, how do we queue into the GPUs, how we can queue. There is an architected queuing language, and we have a flat memory addressing from the CPU and the GPU. We have a way to atomic memory transactions, do the atomic memory transactions where we have we can do transactions between CPUs and GPUs. And we can have, there is a way to define process concurrency and preemption. Now, the essential point here is because it's a standard, the HSA is a standard, it's a specification which is accepted by many companies. So once you write your software on top of HSA-enabled software, it can run on any other platforms, not just AMD. So it is sort of a standard. So that way, that application becomes portable. The next rectangle, which is in the bottom left, which is what are the support for the developers. So we have LLVM based GCN compiler. GCN is our graphics core next. Our GPUs, the new recent versions of GPUs are called graphics core next, which generates ISA code from various languages, which I'm going to talk in the next slide. We have offline compiler support, standardized loader code formats. We have assembler and disassembler obviously in the stack, and of course full documentation. And the last rectangle on the bottom right, we sort of we claim and then we say that it's all open source. It's a set of libraries, deep learning frameworks, optimized parallel programming frameworks, and then the profiler and GDB. Everything is on open source, and it is available on the ROCm software platform, which I'm going to give the link later. Yeah. Now, one of the essential parts of any software stack is what are the compilers, what are the languages that you support on your platform. Now, we support several languages, but we have mentioned the 3 important ones. Let me start from the left. The first one is called HIP. HIP is not a language per se, but it is a tool to convert the CUDA code, which is the NVIDIA's CUDA code, to portable C++. The idea is this: if you have, of course, NVIDIA is a pioneer in GPU compute, and there are several applications, including deep neural network applications, which are already ported onto CUDA. Now we enable those applications to be ported easily without too much of effort to AMD GPUs using this HIP compiler. Basically, as it says, is a single source, and then we have a single source host plus kernel. So because it uses the C++ kernel language, we have a single source. CUDA has 2 sources. One is kernel source, and the other is host code. We have only single source in the C++ language. And then the advantage is that it's the same code. You don't need to write separate code for AMD GPUs and for NVIDIA GPUs. It's the same source. You can maintain one source with the HIP, which is enabled by HIP, which can run on NVIDIA and the AMD GPUs. So when to use this language? So we recommend this to be used when you want to port existing CUDA code. For example, let's say you have Cafe code, which is written in CUDA. You can actually port it using HIP. Then the developers who are familiar with CUDA, maybe you can write it there and then convert it into which can run on AMD. And then, of course, new projects that need portability to AMD and the NVIDIA is maybe another reason to go to HIP. The second language which we support is called HCC, Heterogeneous C++ Compiler. It's again a single source host plus kernel language. Actually, HIP converts that to HCC. Basically, you may be aware that C++ and the OpenMP standards are also enabling GPU compute. So we have latest standard C++ 17 and C++ 20 standards which have a GPU support. So we have the compiler which supports those constructs in C++, which runs on the AMD GPU. So that's HCC. We'll talk a little more on that. When to use, for example, when you the biggest advantage, as I said, it is the single source. I mean, you don't need to have separate source for kernel, separate source for host, and then like OpenCL, the one which is written on the right side. So there, where we have a separate source for which runs on the CPU, and you have to make a call to runtime call to the GPU, and the GPU code has to be written in another C99 kernel language, etc., etc. So people have sort of thought that that's not a very nice way of writing the code. So C++, that problem is solved, where you have a single source, and then we just to do an offload from the GPU. Wherever you want to offload, you can just use some constructs of the C++ language, and then you can offload that kernel to the GPU. So when to use it, we have when we are familiar with C++ language, and you can actually write it very easily, and then you can use any C++ compiler and then compile that which has this which recognizes these constructs. The third one, which I think I'm sure you all know, OpenCL is a Chronos standard, which of course one inelegancy there is a separate kernel and then host. It's C99 based kernel language, and then it supports CPUs, GPUs, FPGAs. Of course, we have OpenCL is there are a lot of code has already been written in OpenCL for CPUs, GPU, and FPGAs. So we support all the three on our ROCm stack, and if you have any applications written any of these three, it runs seamlessly on our platforms. When I say AMD platforms, we have AMD CPUs and AMD GPUs. It can be we can use it for both. Yeah. So this HCC, we have used CLang or LLVM open source compiler to make sure that it is sort of open source, plus it's a standard, well-known standard compiler, and single source for CPU and GPU. I explained that, and we have the performance optimized for accelerators. We have explicit and implicit data movement. C++ standards give you one disadvantage of accelerator, one inelegancy of accelerators is that we have to explicitly manage your data. So you need to send the data from the CPU memory to the GPU memory. It can be either explicit or implicit. So we support both there in the language. And we have scratchpad memories, which can be used in the GPU world, where you can do some computations on which you can keep close to the GPUs. Asynchronous commands can be issued. You can have launch the kernel, and you don't need to wait from the CPU side. You can actually do asynchronous launch, and then you need not wait for that. The dialects are some of these constructs. I mean, of course, C++ standard has evolved. So we have accelerator feature, accelerator view. Accelerator actually defines the GPU. Accelerator view gives you the memory or the view of the GPU, and the completion feature or actually asynchronous command, which can say that when the GPU completes, you can notify. The kernels are launched using what's called as parallel for each, which when you write a loop in the OpenCL, you write as a kernel, and then you write the loop there, and the loop body there. In this case, you have explicitly say parallel for each, and then which means that has to be executed in SIMD fashion on the GPU. For example, you have a convolution kernel, you can write as a parallel for each, and then it can be launched on automatically it gets launched on the GPUs. Yeah, as I said, it's a C++ 17 standard, and then we have support for OpenMP also for parallel. Yeah. Sorry. Yeah, sorry. Yeah. So the biggest one of the biggest challenges for writing GPU applications is that we need to write both we need to write one code for the host and another code for the this accelerator. In this case, in our case, we, as is shown in the figure, we have one front end which takes both the CPU path and the GPU path. For example, if you look at the right side, it is the CPU compiler which compiles for the CPU and then generates the CPU code. On the left side, you have the GPU code, which is compiled using the GPU compiler, and both are clubbed together. And the GPU code on the bottom runs on the ROCm runtime, ROCm stack, ROCm driver, which I was explained, and it uses the ROCr system runtime APIs, and then it runs on the AMD GPUs. So that's how this GPU runs, and the CPU obviously runs on the Linux native code. So that way we bundle both CPU and GPU together. So you don't need to have a kernel separately and host code separately and use the launcher to launch the GPU code. So GCN compiler directly converts to the GPU ISA, and then we have documentations for the GCN compiler, LLVM, CLang, LLVM, and GCN assembler. We support both Linux and Windows, though Linux is shown here. So the advantage of this stack is that everything is open source, like the compiler, the GCN architecture, the ISA, the whole flow is complete, and then the driver, AMD GPU driver, ROCm driver, all are open source. I'll give the link for you to try out. Yeah, so let us just quickly go through some of the features, and then we'll move on to the DNN frameworks. We have strong support for HIP features, which is HCC and then the HIP converter. Strong support for most commonly used parts of CUDA APIs. I'll show you in the next slide how we have a mapping from CUDA APIs to our APIs. Streams, events, memory allocators, deallocators, profiling. HIP also includes driver API support modules and context. C++ support includes templates, namespace, classes, and lambdas. So the complete C++ support. This is C++ compiler anyway. It supports C++ 11, 14, and 17 features. The third bullet says that HIPified code is portable to AMD, ROCm, and NVIDIA code. That's the beauty. So if you have a HIPified code, when you run through our compiler, the code generated can run both on AMD as well as NVIDIA. If you have a CUDA there, it can run on CUDA, or it can run on AMD or with ROCm. And the CUDA developers can use native CUDA tools. You can just use the same NVIDIA toolset. And the ROCm, you can use our toolset like HCC, ROCm Profiler, and then CodeXL. So HIP also has, like CUDA has, we have HIP BLAST, HIP FFT, HIP random number generator, and several other high performance libraries for our GPUs. The last point is that HIPified tools automated translation from CUDA to HIP, so that I can show you in the next slide. Yeah, so let us take one example where, for example, this is taken from the Cafe DNN framework code. So this is the existing CUDA code. Now, if you run through our HIPify compiler, it actually automatically converts them into the way it can run on the AMD GPU. So it's actually HIPified. Because essentially, you can see except for the yellow ones which have been changed, the rest is exactly the same. So it actually changes the way we call the block index, and then the launch parameters. A few small changes are done for this at the source level. We do some changes, and this HIP code we claim that it can run both on CUDA as well as on the ROCm. As you can see, there's not much changes done. We can actually do it by hand, but if the code is very, for example, Cafe has some 10,000 lines, it automatically can be done within by using this tool. Now, this is a C++ lag feature unchanged. The math library is unchanged. The index is the way it is called. Computation is done. The other example is the CUDA runtime APIs, again taken from Cafe. Now you have async GPU push. So you can call, instead of CUDA stream, we call HIP stream. Instead of CUDA device, you say HIP get device. For example, CUDA malloc is converted to HIP malloc. CUDA mem copy is made as HIP mem copy. Actually, this HIP is actually a sort of a template, or it is a interface to call either the CUDA or the ROCm equivalent. So we have some sort of a common interface which can call CUDA or ROCm depending on the platform. Now the tool usage is very simple. You take the CUDA application, you call our Hipify, and then 99% it gets automatic conversion. And the developer may need to do some cleanup and some tuning, which is there in the documentation, what you need to do. And then it converts into portable C++ compile C++ code. Developer can maintain this, and then resulting code can run on both NVIDIA and the AMD GPUs. Now, how do you run it on NVIDIA and how do you run it on AMD GPU? So on the NVIDIA case, you just have to include a header file, a HIP to CUDA header file that actually converts the HIP APIs to CUDA runtime, as you can sort of guessed it. And compute kernels mostly unchanged because there's the same CUDA code. It just runs as it is, kernels plus CUDA APIs. And you use the NVCC, which is a native NVIDIA compiler, and converts into CUDA executable, and which can be launched on the NVIDIA. Similarly, on the AMD side, right hand side, you include HIP to HCC header, with this API is implemented. In this case, we just implement as a small, lightweight HIP runtime, which actually calls our HIP compiler constructs like HC accelerator, which will create the device, logical device, GPU accelerator, and then the accelerator view and then completion. They are just given a few of the APIs there to convert that to make it run on the AMD GPUs. And code compiled using HCC, and we can use AMD profilers like CodeXL and any other AMD tools to run it and then profile it on the AMD GPUs. So you convert it to HCC, and then you becomes HCC executable. It can run on the AMD. So this is a very elegant way of running once you Hipify, you can kernels plus HIP APIs can run both on NVIDIA and the AMD GPUs. Okay, now let us move on to the deep learning and then see how this has enabled some of the deep learning stack. So one example which we have shown, how easy is it to convert, for example, the Caffe, a deep learning framework Caffe into HIP code. So as it says, the GitHub Caffe has about 55,000 lines of code. It's a C++ code of Caffe, and it is GPU accelerated with CUDA, obviously, CUDA and CUDNN. And when we run this through our HIP 99.6, I mean, almost 100%, like except for a very few lines, about 200 to 300 lines, everything is automatically converted into HIP. And it also marks those code which cannot be converted into one, and those has to be done by hand. Otherwise, everything should be ready to be running. Porting requires less than 1 week developer's time, and supports all Caffe features, multi-GPU, P2P, FFT filters, etc. HIP Caffe is fastest Caffe on AMD hardware. We have several ports of Caffe on AMD platforms, including Caffe OpenCL. And we found that this is one of the fastest running Caffe on AMD GPUs. And the right hand side, it shows that the complexity is significantly reduced because we convert that into we will use HIP, and then very few lines of code has to be done manually. So let's say 200 or 300 lines. Now, so what are the DNN frameworks which is available on ROCm stack? One thing which we have observed is once we do Hipify, still it's equivalent of CUDA. I mean, if you look at the way NVIDIA has done the Caffe, the CUDA port, there is a CUDA port which is done by the community, including TensorFlow. There is a CUDA port which is done by the community. There is a CUDNN version also, which is a high performance version. I mean, it can run much faster than CUDA. Essentially, CUDNN is a natively written DNN library, which has APIs which are at a higher level than CUDA APIs. For example, CUDA has matrix multiplication, matrix matmul, but CUDNN has an APIs like convolution forward, convolution backward, etc. Now we have realized that the importance of that, and then we have come up with MI Open, which is our MI cards. I mean, our brand name is MI cards for AMD GPUs for machine intelligence. So the MI Open is roughly equivalent of CUDNN on NVIDIA. So it's accelerator library for supporting DNN frameworks for AMD on AMD GPUs. The link is there. You can search for MI Open in the Google, you'll get it. And that library is has to be linked with the HIP cafe, which is converted through HIP, and then you can that accelerates almost like some 10 to 15 times, which is from HIP cafe. And MI Open interestingly has both HIP and the OpenCL backend. You can use both OpenCL backend, HIP backend, depending on the application needs. The second bullet is a HIP cafe, which is ported on AMD ROCm 1.7. We have this cafe running on AMD platforms, which has MI Open backend as well. It is there on the link which I've shown. And we have seen the significant performance boost with MI Open, as I said, some 5 to 10 times faster. If you look at TensorFlow, we have TensorFlow 1.3 ported on AMD ROCm 1.7. Of course, TensorFlow already is released 1.7 and they're going to 1.8 now. But we have 1.3 port running on AMD GPUs with ROCm 1.7. Again, it has enabled with MI Open backend, HIP backend. We have other frameworks which are done by some community, which is Paddle, Cafe 2. We have some versions of Torch and a few more to come. If you can just go through a ROCm software platform, search for ROCm software platform, the GitHub, it has all the work which has been done on ROCm, which on AMD GPUs. You can have a look at it and then download, try it yourself. You can contribute, etc. So this is very similar to NVIDIA stack. I just want to make sure that you are aware of. We also have almost like AMD also has a similar stack. So at the bottommost, we have the Radeon Instinct card. The Radeon Instinct is the DNN equivalent card. The difference between this and the other AMD GPUs is this doesn't have any graphics. It's only for compute card, like Tesla card for NVIDIA. So it's just meant for compute server card. That uses obviously the ROCm platform, the ROCm driver. On the next one, that is HSA enabled. HSA is a heterogeneous system architecture, which is this open spec for GPU compute. And we have HCC, and on top of that we have HCC, HIP, OpenCL, and we have Python backend also, which is all based on LLVM. So that is the ROCm stack, which is available on open source. That is essential for interfacing to our GPUs as well as to use various compilers on our device. On top of that, we have middleware and libraries, which are accelerator libraries. One which I talked about is MI Open, which is equal to CUDNN. And we also have libraries, accelerator libraries, math libraries like a BLAS, FFT, random number generator, etc. So some of these libraries can be used for DNN as well as for some other HPC application, high performance computing applications as well. So it's not, this stack is not just for deep learning. And then we have various frameworks ported. Not all of them are ported, but we just mentioned that TensorFlow is ready, Cafe and Cafe 2 are ready, and Keras on TensorFlow is of course runs. Torch is still, I think we have some issues there. I'm not sure about MXNet. So, and then you can run machine learning applications on top of this framework. So that completes the stack, and all these is there in the GitHub, which is on the ROCm platform. So I don't know why it says it's. Sorry. So this is the ROCm software platform website. I just given a screenshot just to give you an idea of what we have there. So we have HIP Cafe, ROC BLAS, ROC FFT, MI Open, TensorFlow. And if you look at all the pieces, you have all the list of all the things which are ported on AMD GPUs on ROCm. And we can have a look and then try it yourself on AMD GPUs. I think there is a question, but anyway, I'm more or less done. We can take questions maybe. Yeah, so let me just conclude. So AMD has a true open source software stack for the GPU compute. I mentioned it's GPU compute because the stack is actually for any compute. It need not be deep neural networks. Of course, deep neural networks is one of the major targets for us. AMD ROCm is high performance open source platforms of software development on GPUs. So high performance software, basically high performance computing and deep neural network applications. Of course, you can't run something like Java on this because it's mostly for high performance compute. We encourage developers to exploit the platform on the DNN GPU compute, which is completely open source. You can contribute to any of these stack. Several, as I said, several frameworks, deep neural frameworks are already ported and ready to use. You can go and we have tried, we have used this for various training and inference purposes on various small and high-end GPUs of AMD. That's it, Vivek. Let me take few questions. Okay, I can see one. Let me go through questions now. Okay, so the one question I can read here is whether all kinds of neural networks like ANN, CNN, RNN, GAN support. That's a very nice question. So no, right now we have support for CNN. We are getting ready for RNN also because some of the APIs are missing. So if you already have RNN, that can be ported using HIP. That may not run that well. We need MI open support, like equivalent of CUDN support. So RNN does run, but if you need high performance, much more higher performance, then MI open has to be enabled for RNN because there are some APIs which are missing in MI open for RNN. So to answer the question, yes, support is available, but if you need higher performance using like CNN, we need MI open support for that. GAN is also same thing. So we don't support high performance things are not supported. So CNN support. So we have all these ImageNet networks like AlexNet to ResNet 50 or ResNets running on our AMD GPUs, and then we have I think we have published some performance numbers as well on AMD Vega. Vega is the latest card which is released on by AMD, Vega 10, and the Vega 20 is coming up, which is sort of competing, which is about 10 teraflops card and 16 GB memory, and then we have published 64 compute units card. So we have run some training, all ResNet and Google Nets on that, and then we have got some impressive numbers. I don't see. Okay, sorry, there are some more questions, I guess. Okay, sorry, I missed it. Okay, one more question. Do we distinguish the CPU code and the GPU code in the source, or how is that done? Okay, that's again a very nice question. So the way it is done is that ideally we would like to not differentiate. I mean, ideally, I mean, if you look at a high level for a application writer in a DNN application writer, he may not want to know. I mean, he may not know, he or she may not know, or she may not care which runs on CPU and which runs on GPU. So he would like to write a Python code, and he expects the runtime to make a decision on running on CPU and GPU automatically, right? So we don't need to worry. For example, the deep neural network application writer may not even care whether CPUs are there, GPUs are there, how many compute units, what is the memory, etc., etc. That's all matter of detail for him, and he may not bother because he has his own problems. But the issue is, even today, with even such a mature technology, we are unable to automatically do that without developers' help. We can't automatically schedule on the CPUs and GPUs. So to answer the question, the developer has to say this part has to run on the CPU, this part has to run on the GPUs. That developer has to do both on NVIDIA and on the AMD GPUs. The compilers are not mature enough to make the decision automatically. Now, for the for the OpenCL case, it is very simple because host code is very clear, and kernel code, whatever starts with kernel, runs on the GPU, so it's very clear. For C++, we have what's called as accelerator class. When you put it as an accelerator class, that's the compiler understands that, okay, whatever is there in the accelerator is meant for the GPU, and then you write for parallel for each, and it understands that those are the kernels which has to be launched on the GPU. So basically, essentially, the developer has to tell this has to run on the GPUs. So that's the long answer for that. The another question is, do you have always write code in CUDA before it can be converted into HIP code? Yes, HIP is essentially a converter from CUDA to HCC, our native source code. If you want to develop a new application, you need to write using C++ or OpenCL on AMD GPUs. If you have already an application using CUDA, then you need HIP. Otherwise, if you write in C++ or OpenCL, you don't need HIP. So if you directly, you can. I think, yeah. That's the other question. So in TensorFlow, it supports writing distributed GPU apps for scale. Possible with AMD GPUs? That's a good question. We have tried up to 2 GPUs with TensorFlow, and we have shown the scaling very well. I think up to 4 also. I'm not sure. I can have to confirm that. But yes, we support. See, this multi GPUs again is done by the developer or the frameworks. So TensorFlow automatically schedules TensorFlow. It takes as a compute graph, and then it automatically it can schedule this into various GPUs available. In fact, it can do on the cluster of servers as well. So all it needs is the APIs to schedule it onto GPUs. So those APIs are available in AMD GPUs also. Yeah, so that works on AMD GPUs, but we have not tested with maybe 10 GPUs or maybe 18 GPUs. But I think it scales. The issue is technically it is possible. The problem is if the workload is not very well parallelized, and then if there is too much of communication between those parallel parts, then it may not scale well. So that's the issue right now. So up to 4 GPUs we have seen scaling very well. Beyond that, I don't think we have tried this thing. And scale out option, like what I was saying, hyperscale, I don't think we have tried with more than some 4 servers which have each having 2 GPUs kind of thing. It's not more complex. I think I have answered all the questions which are there. Yeah, Vivek,
There are a few more actually. I don't know if you can see them. Uh, can you see other questions, or shall I recite them to you?
Yeah. You can say I don't see.
Okay, let me just speak them out. So one question is, can we run our Python-based CNN applications on AMD GPUs?
Yes, good question. So Python-based CNN, I think it has to be either on the Cafe, or I'll be using PyCafe or TensorFlow. I think one of these. Or is there any other way? I mean, I can. I'm guessing. I'm assuming that it is TensorFlow or PyCafe. Yes, because we support TensorFlow. Whatever today you can run on TensorFlow using Python or C++ can run on our GPUs also. And there is another way of running Python. If you can write your own code for convolution using the NumPy APIs, we can actually support that as well on the AMD GPUs automatically. You don't need any TensorFlow or anything. You can directly run Python on the GPUs also. That stack also is available.
Okay. So
next.
Yeah, the next question is, do you have any benchmarking statistics of AMD GPUs versus NVIDIA GPUs in terms of runtime, memory, accuracy, etc.?
Yes, that's a good question again. So yeah, so I deliberately did not show some of the comparisons, because this slide, that those data has to be certified by the AMD legal. I didn't have the time. So what I would encourage you to do is you can look at the website which I shown. We have given some performance data there. We have a lot of performance data which is comparing AMD GPUs versus NVIDIA GPUs. Essentially what I would like to say is the GPUs are very similar. I mean, if you look at the Tesla cards which NVIDIA has, and then AMD GPUs, the performance wise both are similar. We have similar in terms of the theoretical peak. It is just that the software which can exploit that performance and then give it without what efficiency. So we have seen our performance is on par with up to Maxwell, and then of course the Pascal is slightly ahead. So somewhere roughly between Pascal and then somewhere between Maxwell and Pascal. Yeah. The exact details can be seen in the website. Yeah.
Okay, thank you. The next question is, how do we decide whether we need to go with CPU or GPU for machine learning applications?
Okay. So that's a good question again. So for machine learning, it's sort of well known that GPUs are the right choice. I mean, I don't know why. In fact, Cafe, if you remember, that doesn't support it. It was not supporting CPU. TensorFlow doesn't support. It was not supporting CPU at all. The reason they were saying was, why do you want to run it on CPUs when GPUs are there? Basically because As you know, the training, deep learning training spends about 80% in convolutions. It's mostly in 80% matrix multiplications, tensor multiplications, which are very apt code for GPUs, because we have SIMD engines with 64 CU SIMD engines, which can run much faster than the CPU. Even if you look at Skylake, which is Intel's latest CPUs, let us say 112 threads CPU, the GPU, which is at 10 teraflops or 12 teraflops GPUs, beat even Skylake, which is the latest Intel processors, by something like 20-30 times. So it can run faster, 30 times faster than Intel's basically because it's very well tuned for matrix multiplication kind of thing. It can run some thousands or 10,000 threads in parallel, so it can beat CPUs hands down. So to answer, nobody would like to do on the CPUs for training. Okay, but for the inference, inference probably makes sense, because you may not want to have huge GPUs on something like a security camera where you want to just run the inference. You may have to have some 2-core or 4-thread processors on the security camera which does the inference. There perhaps you need just the CPUs. That's good enough, because training is mostly a lot of multiplication, a lot of matrix multiplication. For inference, it's much more simpler. So the only latency is the issue. So if we can do something like 1 frame for 40 milliseconds, that's good enough. Even for GoogleNet, we can do by 40-50 milliseconds for some CPU. So to summarize, GPUs are the ones which for training. For this, that's again my personal opinion, and the CPUs for probably inference, and we can have small GPUs also for inference.
Okay, so next question is, some of the laptops are sold with inbuilt GPUs and being used for, practicing deep learning applications by developers. Right. So are there AMD laptops with AMD GPUs which allow the same thing with, let's say, TensorFlow on home laptops or personal laptops?
Good question. Yeah. So our AMD, it's called AMD APUs, which have the same SoC as both CPU and the GPU. That can be used for actually, in fact, I do the same. I run some TensorFlow on our hip TensorFlow on our AMD GPUs, which is built into laptops. It's possible. Of course, you will not get high performance because they are very small. For example, to compare that AMD Raven Ridge, which is the latest APU which we have, has about 12 CUs, 12 compute units, while the Vega 10, which I'm talking about, has 64 CUs, which is about 5 times or 10 times faster. And the number of processing elements are also much larger. So obviously you will not get that performance, but if you can somehow use both CPUs and GPUs of a laptop, you can definitely do much better than, much faster than without any GPU.
Okay, thank you. Folks, any other questions? Give it just another 30 seconds. If you want to ask a question, please put it in the chat window. Okay, I don't see any other questions. So thank you, Dr. Prakash. Thanks for your time, and thanks, audience. This is it. Dr. Prakash, any closing comments or anything?
Nothing. Thanks a lot. Just want to highlight that please go and try AMD GPU compute. Just search for ROCm software platform, and then you can get the link if you have all the software. I would urge you to try that software or AMD. Thank you very much. Good night.
Thank you, Dr. Prakash. Thank you, audience. Thanks for attending.
Thanks. Bye.